Clear.
Okay, so I will start. So hi everyone, I'm Ying Xu from Jinan University. So I'm very glad to have this chance to share with you some experience of me working with ERG during those past few years. As you can see from my background, actually I'm not an ophthalmologist, but I have years working on video information processing through the electrophysiological recording. Like during my PhD, I work on cat's visual cortex through single unit recording. And during my postdoctoral research in Penn, I started working on rodent retina, so by ERG recording, which I'm going to introduce today, and also the whole cell patch from retinal bipolar cell and ganglion cells. So after I returned to China, set up my lab, I built up a platform for recording, including a patch system and multi-electrode array system, and also electroretinogram systems. And as students found that ERG system actually is much more similar than the other two systems to do a recording. Students prefer to use this ERG system to record the retinal light responses instead of using other two because it's easy to operate. The other two is lots of training. So the students always like just take a few times training, they can master how to do the ERG recording. But then I realized that many times those students know how to do the recording, they don't have enough knowledge about the basic principles behind this. So that's why actually I hold these seminars to my students before, seminars contents before, and also the aim of this talk is to introduce some basic principles of the ERGs. So the students, aim for the beginner of this ERG recording. And so they hope for after this talk, they can know some basic knowledge of ERG, and that can help them understand more about the project and help them to design experiment. So what is electroretinogram? Short for ERG. So ERG is a diagnostic test that measures the electrical activity of retina in response to light stimulus. So here is a typical setup for clinical ERG test. There is a gun field or light stimulator in a ball-like shape, and the patient sits in front of the stimulator, and there on his cornea there's the electrode like either type of a shape. There's a corneal electrode that records the light response from the retina, and then a reference on ground. The signals could be catch up by the amplifier and sent to a computer. And so the waveforms of the retinal response to a stimulus could be recorded. And from across different species, all the ERG forms have similar shapes. Like there's a negative peak and followed by a positive peak and so on. And so the characters of the ERG recording is it measures the retina or the function of retinal pigment epithelium. And it's most important, it's non-invasive. And so electrode is put on the cornea, and so besides the scan field that can give the full field flash, there's also LCD monitors that can present you a pattern stimuli. And in clinical, it's commonly used to diagnostic of retinal disorder. And actually for the electrophysiology of vision, besides ERG, there are also several other types like the visually evoked potential called VEP, which measure the cortical response to visual stimuli. And also there's electrooculography, which measures the eye movement. And also electrostachygraphy measures, which measure the nystagmus. As most for the retina, most commonly used are the ERG and VEP. So I'm going to cover these two methods like in the following series. So today's outline, first I'm going to introduce a little bit about the recording system, and then spend major time explaining the origin and factors affecting the flash ERG recording. And there are also some principles behind the pattern ERG and multifocal ERG, as well as VEP, which I'm going to cover in the future seminar. So first, the recording system. So this is a typical ERG system by Roland. So there is a gas field stimulator and the animal table, which has a which can be heated up by like water pump, and the amplifier and connect to power computer and power box. Besides the gas field stimulator, which can give you full field stimuli, there's also a patterned LCD monitor that can give you a patterned stimuli like this. And for the multifocal system, it's different. Besides the monitor, the main computers, there is the LCD monitor that can give you the pattern. But in Roland has another system called SLO, which is a scanning laser ophthalmoscope. It can locate, by this SLO system, it can locate the founder's target in real time. And also through its built-in graphic stimulator, it can present stimulus on the founder's target area. And then those responses can be recorded for each different areas. So that's a multifocal system. And so after the brief introduction of the system, then I'll start talking about the flash ERG. So here you can see examples of flash ERG traces from different species like turtle, toad, rabbit, and human. And for all the ERG traces, there is a typical waveform of a negative wave after the light onset. It's called A wave. And following this, there is a positive peak called B wave. And if the stimulus is long enough, there will always elicit a D wave after light offset. And also during the light on, there is an uprising peak called C wave. So all this information actually can be found through web video at Jinan University. This is a very good, useful website, and you can check more information there. And actually, the ERG was fully studied back in last century. And actually, in 1967, the scientist Ragnar Granit actually won the Nobel Prize for his research, for his work on the ERG. He identified several components of ERG, which shown in black trace as a raw trace of ERG. He found that as a anesthesia state deepening, there is a different wave show up. So he isolated them as P1, which kind of purple or yellow, and the P2 red color, and P3 is blue color. And now it's commonly accepted that negative A wave is the leading edge of the negative P3 component. And the positive B wave reflects a summation of P2 and P3. And slow C wave is a summation of P1, and P3. And those components I will explain later, again, during analysis. And so the electric basis of ERG recording actually is quite simple. So when the light flash on the retina, so the retinal neurons will give an electric signal. The signal, electric current, will flow out of the retina, out of the vitreous, out of the cornea, and through the choroid and the pigment epithelium and the back to the eyeball. So when we put the electrode on the cornea, we can record the current on the part B pathway. So that's electric basic of ERG recordings. And then, but how to explain the origins of the ERG waves? And so this is a major part I'm going to cover today. So that is the cellular origins of ERG waves. And again, this is a typical ERG waves during the short flights and the long flights, A, B, C, D, and also on the rising phase of B wave, when the light stimulus is strong enough, there is oscillate potentials, short as OP. And here is some of the cartoon, which actually later I will explain details and how they get those results. And this is also a cartoon that I will suggest every student to memorize this, to remember all those things. So the principle simpler is A wave arises from photoreceptors. And the B wave came from the mural cell and bipolar cells. And later I will show that documents support the B bipolar cells origin of B wave. And the C wave mainly came from pigment epithelium, and the D wave came from the off bipolar cells. And OPAs arise from amacrine cells. So this is like typical, the classic one. And so now I'll spend a few slides explaining the secondary origins of each wave, including some experiment proof. So A wave, first A wave, here shows the A wave under dark adaptation of called scotopic condition, and also under light adaptation called photopic condition. And you may notice that A wave is smaller under light adaptation. And where does A wave arise? Actually, in clinic, in an experiment, early experiment like back in 1978, so scientists found that when they isolated the retina and add the aspartate in the isolated retinal perfusing, which block transmission from photoreceptors to bipolar cells, only the P3 component of the A wave remained. That means this wave came from the photoreceptors since other neurons pathway was blocked. So this is a basic principles, basic experiment showing this. And also in clinic, when photoreceptor degenerative disease, A wave disappeared. The example shown here is a patient with a retinitis pigmentosa, where you can see there are lots of pigment deposit, and also has a retinal atrophy. And the patient with this RP and all the traces, like actually ERG traces, actually A wave disappear compared with normal people. So that's a solid data to show that A wave actually came from the photoreceptors. And the next, the B wave. Again, the B wave, the origin of B wave came from the clinical discovery that in patients of congenital stationary light blindness, where they have a malfunction in neurotransmission from rod and cone photoreceptors to the bipolar cells, the B wave disappeared. And here you can see that only for negative peak, A wave remained, but A wave still normal, but there's low peak, positive peak, or low B wave. So the clinical, in clinical, they found that okay, the B wave may possibly came from the bipolar cells. So there are different types of bipolar cells, on and off. And so the scientists working on the animals found that when the on pathways is blocked by like intravitreal injection of L-glutamate or this agonist APB, again, the B wave disappeared. That means those pathways, the glutamate pathway, actually the metabotropic glutamate pathway receptor is blocked. When metabotropic glutamate receptor is blocked, the B wave disappeared. And then later, Noga Madi from University of Pennsylvania, where I used to work as a postdoc in her lab, she has been working on the on-signal pathway in the retina, and she found that when G-alpha-O subunit, which is specifically expressed in on-bipolar cells, when this G-alpha subunit was knocked out from the lockout, the mice won't have any B wave at all. So all those data indicate that the B wave actually arise from the on-bipolar cells. And then next, C wave. And remember in the previous slide, I showed a serious experiment. And so actually when people record from the I cup, there's clear A, B, and then C wave. But when they isolate the retina from the RPE, the C wave disappeared. So that indicates C wave actually came from the RPE or retinal pigment epithelium. And also in animal models of AMD or aged macular degeneration animals, where they have a typical symbol of like damage of RPE, so the C wave will also disappeared. And in this paper, they use sodium iodide to cause the injury of the RPE, and then we found that the C wave diminished compared with the normal mice. So C wave arises from the RPE. And how about the OP? So remember that OP actually only appeared when the flash intensity increased. So it has the OPS has a higher response frequencies. So when you use a high pass filter to remove A wave and B wave, you go to the OPS, you go to oscillator potential. And so data shows that OPS actually reflects the current between from the inner retina, especially the endocrine cells, and the OPS in clinical. Scientists found that in patients with ischemia, have a retinal ischemia, like a central retinal vein occlusion, like CRVO, or the diabetic retinopathy, though the A and B wave remain normal, the OPS disappeared. Also, when the intraocular potential, intraocular pressure increased, like from 10 to 70 millimeter high, and so the OPS also disappeared. That indicates the OPS actually came from inner retina, especially the red endocrine cells. And then next, D wave. So D wave, the experiment, D wave appeared only at a long duration of the flash, like more than 100 milliseconds. And so this study shows that when add DNQX, when they inject the DNQX intravitreous, which blocks the AMPA receptors, the D wave disappeared. That indicates that the D wave arises from the AMPA modulate selective transmission, which is between the photoreceptors and off bipolar cells. And so the D wave is different across species. So in principle, the D wave is larger in species having many cones, like the human, cat, and also in one of my early studies, when we compared gerbil, two rodents, compare the gerbil and mouse. The gerbil is also rodent, but has more cones than mouse. Is active during the day. So the gerbil, which have more cones than mouse, they have a clear D wave. So the D wave arises from off bipolar cells, and it's larger in animals having more cones. And besides, so A, B, C, D, and OPS are a few major components in the ERG. But besides those like typical ERG components, there are also a few components that you can test with when you modify the test condition. Like this called scotopic threshold response. But when we present animals very dim light stimuli, which is well below the threshold of A wave. So there is a slow corneal negative peak, a potential to be recorded. So that's called STR. And also the STR could be diminished by after adding GABA or glycine. So that indicates that STR originates from the retinal cells that release glycine or GABA in the dark. And also, I think it's possibly the inner retina, including endocrine cell and ganglion cells. So that's early study. And then more studies showed that STR is reduced when inner retina gets injured. Like example is one here is like during high intraocular potential pressure, when they increase the IOP, the STR diminished compared with the normal eye. And also after the transect to the optic nerve, the STR is also decreased. And after the injected beads to induce glaucoma, which causes like injury on the ganglion cells, that you can see that the AB waves kind of relatively normal, but OPS, the amplitude of OPS decreased, and also the STR amplitude decreased. So those data indicate as STR originates from the in the retina or mainly the ganglion cells, because when you transect optic nerve, it mainly affect the ganglion cells. So STR is one way to measure the ganglion cells response. Besides STR, there's also a photopic negative potential, short as the PHNR, that can reflect the response of ganglion cells. So here is a typical example of PHNR, which is a negative peak following the B wave under photopic conditions. And in clinical, when they test the PHNR, they use blue background and present the red flash. And studies found that the PHNR depends on ganglion cells activity and also is reduced in glaucoma and during retinal vein occlusion and or after optic nerve transection. So here shows example of patient with primary open angle glaucoma, and can clearly see that the huge PHNR recorded in the age match control disappeared in the POAG patient. And also in patient with retinal vein occlusion, you can see that in the affected patient, there's no PHNR, but in the unaffected or normal age match control patient people, and there is clear PHNR. And also in patients with severe diabetic retinopathy, from mild to moderate to severe, and you can see that PHNR decreased. But other response, like a cone response, 30 Hz flickers, or rod response, they all remain normal. But again, you may notice that actually OPS also decreased. So I would think the OPS reflects response from both amacrine cell and ganglion cells. And also here you can see that in an animal model with high IOP, both PHNR decrease, and also both PHNR and PSTR decrease. But the AB wave remained normal. And also in a rat model, after the optic nerve was transected, there is a clear, this is after the optic nerve transection animals. So basically the B wave, the PHNR is kind of much more decreased compared with normal rat. So all this data supports that the PHNR actually originate from the ganglion cells. So after explaining list all the experimental data, so here is the sum up of cellular oranges of ERG. Again, I hope the students can remember this because it matters when they design the experiment or when they want to test which kind of neurons get affected. So you have to pay attention to which kind of waveforms they want to measure. So again, here, A wave came from photoreceptors, B wave originated from unbipolar cells, C wave came from pigment epithelium, and D wave came from the off-bipolar cells. Amacrine cells contribute to OPS, and ganglion cells, you can record ganglion cell response by PHNR and STR. Again, this is kind of important. You really want to memorize this. And then after explaining the origins of ERG, I will spend the next couple slides explaining the factors affecting the ERG, because this is quite important for students to carry out experiment, because there are many factors that will affect the amplitude of ERG, and you ignore something and that will give you a mistake result. And so first is state of adaptation. So here shows a typical example of a ERG response recorded during light adaptation or during light-dark adaptation. And you may notice that the ERG trace recorded under light-adapted conditions smaller, the amplitude is smaller than the dark adapted conditions. And also the time to peak is actually faster than the dark. That's because during dark adapted, the response is mainly mediated by rod, and the rod have a slower response than cones. And when we increase the light intensity of the flashes during dark adaptation, and so the response will reflect a mixture of rod and cones. But when we light adapt the animals, the rod will saturate and won't respond to light change anymore. So all we can see is a cone-mediated response. And so since during dark it's a mixture of rod and cones, and during night there's only cone response, so the amplitude is smaller than the dark adaptation. And also, since cone responds faster than the rod, so the time to peak is shorter. So how long should we dark adapt animals? So one study in 2007 shows that when they increase the dark adaptation time from 50 minutes to 31 hours, 2 hours, and 4 hours, the A wave, B wave, as well as the OPS amplitude increased over time. And later, so this is a intensity curve showing these changes, and later to reach a plateau. So that means when you want to test the animals, you really want to dark capture the animals for over 4 hours in order to get a stable result. And so basically, usually we recommend the adaptation time to at least overnight or 8 hours. And second factors that affect the ERG amplitude is light intensity. For example, showing that the ERG traces change the ERG traces under different flash intensities from weak to bright flash. And you can see that as the flash intensity increase, both the A wave and B wave amplitude increase, and also time to peak also becomes shorter. So that's a condition you really want to be constant across all your experiment. And besides all those flash intensity usually can be controlled by the computers. So when we set up a program, you want to make sure that you have set the same intensity. So you are using the same intensity to all the animals. And besides the computer program, there are also some operation practice that we have to pay attention. First is the size of pupil, which is a major determinant of light intensity to a retina. So during experiment, you really want to fully dilate the pupil. And also any opaque optic media that blocks the light pass into retina should be avoided. And also when if animals develop some like cataract or vitreal hemorrhage, those will absorb the light path and reduce the light intensities. So those animals, when you started test the experiment, you want to check whether animal have this problem or not. And those animals having cataract should be excluded from experiment. And the third factor is the color of light stimulus. Like as we know that human has 3 color selective cones, like blue, green, and red cones, which each type has a peak sensitivity to light have different wavelengths, like from 400 nanometer to 600 nanometers. And mouse, there are only 2 types of color sensitive cones. One is the short wavelengths, the other one is the mid wavelengths. And for all animal species, there is only one type of rod which are very sensitive to light at 500 nanometers. So if you present the animal, the human, with different color of the light, like in this case, show example like 600 nanometer light, it will excite the major, in human will excite the red cones and also some green cones, but not the rod or not the blue cones. But in mouse, if you use 600 nanometers, you can see that they only excite a part of the rod and the mid-wave cones. And so in clinic, actually, different color stimulus can be applied to separate the rod pathway from the cone pathways. So example shown here is that when they present a dim blue light or the red bright light, that will excite rod or cone separately. And when you merge compare the two traces, you can clearly see that the cone response have a faster kinetic than the rod mediated response. And so besides the colors that can separate the rod mediated vision from cone mediated vision, there is another way to separate the two pathways by using their different temporal properties, since rod responds slower than cones. So the highest critical fusion frequency for rod vision is about 50 Hz, but the cones can follow flickering stimulus up to 50 Hz. So actually in clinic, in the standard ISAB or international standard protocols, they use a certain frequency of 30 Hz in order to isolate a cone system from a rod system. And here it shows the example of flicker response to a 30 Hz flicker. And also in my work comparing gerbil with mouse, as I mentioned before, the gerbil has more cones than mouse. You can see that the gerbils can follow up to like even 55 Hz of flicker, but for mouse, which like cones, can hardly follow the flicker higher than 20 Hz. So this is a good way to separate cones from the rod pathway. And besides all those factors, there's also one major factor that people sometimes can ignore this, but actually it have a great impact on the ERG recording, that is anesthesia agent used. So this is a recent study showed that they compared the different anesthesia agent effect, the impact on the ERG amplitude. And you can see that the MN Bush component with combination of these three agents, they have larger response than the pentobarbital sodium and ketamine zilizine. And it was also same for the photopic condition and also same for the OPS. So the pentobarbital sodium or the ketamine zilizine anesthesia agent used actually maybe maybe not be the optimal agent if you want to elicit maximum response. And there's also another study recently, last year, showing that they compared the effect of anesthesia agent, including ketamine or trimethyl or TBA, which have commercial name Evertin or Eucerin, and they found they also have different impact on the ERG recordings. So I know that in different countries, when I was in US, we like to use ketamine zilizine, but in China, since there's restricted control, we prefer to use like TBA. And so, which kind of agent you want to choose? And so I would suggest that no matter which kind of agent you use, you want to use the same agent for all your experiment. You don't want to switch the anesthesia agent from one experiment to the other, since we can, as you may see from all this data, that those different agents really will affect the amplitude of ERG. And the last but not least one is the circadian rhythm. As we know that mouse is kind of active during night and during daytime sleeps, and you can. So then you may expect that rest response may also have different activity during night than the day. And so in one study in 2006, actually they found that the photopic response, which is mediated by cone, remember, the cone response actually is larger during daytime, during midday than the midnight. And this data was also further reported by another later experiment in 2008. They also showed that during the midday, the photopic B wave is larger than the B wave recorded at midnight of the mice. And how about scotopic? The scotopic condition, they compared the amplitude across different flash intensities. They found that at a weak flight intensity, basically there was no difference between the amplitude. But at the strong flash intensities, there are clear reason with scopic B wave peaks around dawn and dusk than the midday and midnight. So again, what does it mean? So that means when you compare record from a series of like more than 10 or like eight animals during one experiment, you really want to get all the data like done within a day. You don't want the experiment to last from day to night. Since you can say you may expect the smaller response for animals recording at night. So design experiment well, so you can carry out all experiments either during, you can finish all recording either during daytime or during night. And next is how to analyze the ERG. And the first one is to measure the amplitude and the time to peak of both A and B wave. It's commonly used one, and all the students can easily learn the way to do this. And I would say that the A wave, B wave is a very important parameters, and also it's important to that to show a change of A wave and B wave following a series of net intensities like this. Like here, they plot the amplitude of A wave and B wave with as a flash intensity increase, and they also plot the time to peak as a time light flash intensity increase. And you have multiple, more than like 3 data points along the flash intensity. The data will be more solid than just showing one intensity, that the parameter at one intensity. And also from here, another information I want to deliver here is that you can clearly say that when light intensity increase, both A wave and B wave amplitude increase and the time to peak decrease. So this is a good way to present your data showing the A, B wave and their time to peak. And the ERG analysis that's based only upon the amplitude measurement sometimes may lead to the error conclusions, like if the pupil is not fully dilated. And also, as different labs have different experiment conditions, it's not easy to compare the data. So one way to overcome this difficulty actually is to compare a series of ERG response for the relationship between the A wave and the B wave. That is to calculate the ratio of B wave to A wave. Here shows an example of calculating they plot B wave amplitude against the A wave amplitude. And different symbols represent data from different knives. And you can see that though the absolute value for the B wave is different, but when they calculate the B to A wave ratio or the slope, actually are very similar across labs. But on this step, why do we need to calculate this? And besides to compare data from cross labs, there's another important thing. The important result of calculating the B wave to A wave ratio is actually to identify the site of disorder. Because any disorder that localizes photoreceptors and does not involve more proximal sites like the bipolar cell, ganglion cell, it will be expressed in abnormal A wave amplitude, but a normal B wave to A wave ratio. Again, example shown here is for patient with myopia, which has a problem like reduced function in photoreceptors, but because the transmission is normal, so the B wave to A wave ratio is actually similar to the other animals, to the other lab. But on the other side, if there's a defect in signal transmission from the photoreceptors to the bipolar cells, and that will show abnormal B wave to A wave ratio, but the amplitude of ERG waves may even increase. So example shown here is a congenital stationary night blindness, which I mentioned before, is that they have a defect in the unbipolar cells. And again, you can see that the A wave amplitude is may be similar or even larger than other labs, and the data from other labs, the B wave to A wave ratio is much smaller than the normal one. So that indicates there's something wrong between photoreceptor to the bipolar cells. So when if students present data like this, I will suggest them to stain for the ribbons and for the post-synaptic potentials. They want to check whether the synaptic collection is abnormal or not. So that's the ratio of B wave to A wave. And the next one is to reconstruct of P3 and P2, which is less frequently used in all those publications. But remember that the B wave, which reflect response of unbipolar cells, is actually the summation of P2 and P3. So for the expert in electrophysiology, ERG, sometimes they will ask you to show the true response of B wave or the P2. And so to do this, you have to reconstruct the P3 and subtract ERG, the P3 from the measured ERG. Then you can get a P2 component. And how to do this? It's kind of a little bit difficult. So you have to first give a series of flash intensities. You can record the different traces, and from the leading edge of the decreasing phase of A wave, and you can fit into a function and build up the fit into phototransduction model, and can build up a series, build up the function, and build up the P3 curve. And then you subtract the P3 from ERG, you can get a pure B wave response. And then this, and for the experts in ERG, they believe that this P2 component is actually the real response of bipolar cell. But we're not mathematicians, so it's not easy to reconstruct the function. So most time when people are, especially ophthalmologists, I think, they prefer to just simplify this step and just only use B wave instead of P2 to reflect the bipolar cell response. But you have to know that there is a way to calculate, to accurately find out the B wave response. And for the other components of ERG, like the flicker or OPS or later the VVP, the simple way to measure is to measure the amplitude. To measure those is to just calculate the average amplitude of all those peaks. And for the OPS, there's also a way to calculate the root mean square of the first like five peaks. But actually, in my studies, I think not only mine but other studies, again, the simpler way is just find the peak-to-peak amplitude and average them for the first like 3 obvious peak of OPS. And after, so basically I covered the major components of flash ERG, and now the last part, almost the last part, I will cover something about, I'll talk about the ISET, which is International Society for Clinical Electrophysiology or Wayne protocol. And this is kind of updated nowadays, it keep on updating, and now they are using 6 programs to do this, which include the adapted conditions and 3 flash intensity. The first kind of weak, that only reflect the rod response, and then they increase the intensity to 3.0, and they will reflect the combined red and cone response, and then even stronger to 10. And then also during a adapted condition, OPS will be isolated by applying high pass filter. And then the next adapted the patient and got a cone response, and also then with a 30 Hz flicker, then further isolated cone response. So that's a ICF. And for the recording electrode, I just searched online, found all types of electrode. But I know that recently, since I started to record from monkey, so I found that, okay, so this kind of recording electrode kind of commonly used now in clinic. So, but beyond this ISAF, there are several other procedures you may want to try. That depends on your objective. The first is chromatic electrogram. As I mentioned, that different colors may activate specifically activate different types of cones or rods, and also you can use red color to isolate red from cones. So when you want to test to examine the separate rod from cone, you may want to try the chromatic ERG. And also for you want to reconstruct the A wave or B wave from the raw ERG trace. You may want to increase the light intensities from 3 using ISF to more than like 6 or 8 steps. So you have a series of light intensity response. And so by using this, you can use the phototransduction function and do a model of a photoreceptor current. And then also in our case, if you want to test the off pathway, you may want to use long duration flashes. And also if you want to measure the ganglion cell response, you may want to try the photopic electric response. And also, as I mentioned, like in previous slides, you want to record the ganglion cells, you may also try the STR. So STR is it's really small compared to PHNR. And the last, I'll just use one slide to show the good example of ERG data presentation in animal experiment. So this is one from 2007 paper. So they compare ERG traces from a knockout mice with a control, and then also shows after how they rescue the knockout mice. So the good way, so they present data in a nice way that they align the traces of 3 groups together, use different colors, so you can easily see the difference. And they align all the traces along with the increasing densities, and you can clearly see the response increase when the infraction increase. So first is your example of the raw trace of ERG under scotopic and also the photopic condition. And then the analyzer data presents amplitude of both A wave and B wave with against the light intensities. And then here you can clearly see that the red color means the rescue. So after the rescue, the transgenic mice, the B wave is kind of similar to control. And also it's happening the same at the photopic conditions. So if you have some data like that, I would think it's really solid and we really trust your data. So if you have an animal like that, you want design experiment like that. Okay, last, just after nearly 1 hour's talk, I think it's a take-home message. Again, I have said again that this is the origin of the component, ERG component is really important. Like again, the A wave contribute to arise from photoreceptors. B wave came from unbipolar cells, and the D wave of bipolar cells. C wave came from pigment epithelium. OPS arise from endocrine cells and the ganglion cells. If you want to record ganglion response, you may try PHNR, STR, and later in next seminar I'll talk about Titan ERG. So those are all the things you may want to keep in mind before you start design experiment. And again, when you carry out experiment, you have to remember there are several major factors that will affect the ERG recording. Like first, you want to give animals enough time for adaptation. We would usually recommend like overnight adaptation. And also you want to fully dilate the pupil to allow a full entrance of light into retina. And again, you want to exclude animals developing cataract or visual hemorrhage. And also you want to use the same anesthesia agent across all experiment. And also because the circadian rhythm impact, you want to test animals at a similar testing time, either day or night. You don't want to mix them together. So basically that's all for today's talk about the principles of ERG. For the next 2 seminars, I'll cover the practice of flash ERG recording and also Python ERG as a VEP recording, and some of the principles behind the Python ERG and VEP. I will cover there. So that's all. So if you have any question, you can drop my email at admission@jnu.edu.cn. And so that's all. So do you have any questions?